Okay, graphing two variable inequalities. So last time it was just x. Clearly this time we have y in it also. Remember, if it has the equal to bar or not is important. On a number line, if it doesn't have the equal to line, it was hollow because it wasn't included. On a two-dimensional plane, the boundary is dashed. So dashed is basically the same idea as hollow. If it does have the equal to bar, then you just graph it as a solid line like you would normally. Then you're going to test a point that's not on it and see if it's true or false, and we only shade the true regions. Make sure you shade the true. Do not shade the false. So start as if it says equal to. So this is clearly just a line. It has a y-intercept of 2, and it has a slope of down 2 over 3. Do it a couple times. Do it the opposite direction. But before you connect the dots, that's when you have to ask yourself if it should be solid or dashed. So looking at this equation, there is no equal to line, so it should be dashed or dotted, however you want to think about it. So make sure you connect the dots with a dashed line. And then we're going to test a point. You cannot test a point on the line. So I could not test 3, 0, because that's clearly on the line. Instead, I'm going to test 0, 0. We got lucky. 0, 0 is not on my line. When I plug 0 in for y and 0 in for x, I get this statement. Is that true or false? It's true. Here's 0. It's true. So this side must be the true side. If I was using a pencil, I would shade that in, but because I'm on the iPad, stripes work the best for me. The entire graph, including the shading, is the solution. One thing I want to point out, as long as y is on the left, y less than or y less than or equal to, your y-axis is this red axis. I'm making it red right now. The smaller y's are down here, right? The further down you go, the smaller the y's get. If it says y is less than your equation, you're going to shade down because y's getting smaller are the ones going down. If it says y greater than or y greater or equal to, that y-axis, the bigger y's are up here. So you're going to shade up from your graph. We'll do that some more in some other examples. But if you don't like shortcuts, test a point. That will always work. Okay, start with as if it wasn't equal to. You remember your parent graphs from chapter 1. This is one of those reasons why you're not allowed to forget this stuff. Graph this, it's a parabola, right? Vertex at 0, negative 1. The a value is 1. But before I connect the points, I need to stop and ask myself if it should be solid or dotted. Because it has the equal to bar, this one's going to be solid. So try to draw yourself a parabola with a solid line. Then again, you can test a point. 0, 0 is not on the purple line. I know it's not a line, but the purple curve. So I can test 0, 0. If I plug 0 in for the variables, I get this statement. Remember, it's supposed to eat the bigger number. Is it eating the bigger number right now? Yes, because 0 is bigger than negative 1. So then that means the point I tested, 0, 0, is true. So here's 0, 0, it's true. You always shade where the trues are. So since 0 is inside the parabola must be true. If I had gotten false, the other side must be true. So for example, if you test, because you're allowed to test anything not on the line, 0, negative 2. I can tell you right now you're going to get a false answer. So this side would have been false. So I still would have shaded inside the parabola. Finally, if you like shortcuts, this says y greater or equal. The greater y's are up. So from the vertex, I would have shaded up. which would have still landed me inside the parabola. The whole picture with the shading is your full solution. Okay, but the chapter's on systems, so we're going to make you graph 2 at a time, and then we need to find the solution to the system, which is a common shading. So here we go. Graph the first equation. It's a cubic. The locator point is at -1, +1. Inflection point, because it's a cubic. It has an A value of 1, so 1 over and up, 1 over and down. Before I connect the points, I need to figure out if it should be solid or dotted. This one should be dotted because it does not have the equal to line, and I should try to make it look like a cubic. I'm going to start using that shortcut. Y is less than. The y's that are smaller than my graph, if you put your pencil on the locator point, smaller y's go down. So because we're doing a system right now, you could either draw arrows, little tiny arrows for yourself if you want, or I like to do stripes, or you could do really, really light shading. But we are not done yet, so don't do anything too permanent. But definitely below the cubic is where you would shade for that piece. Now we're going to graph another piece right on top of it. That's a circle. The center is at -1, +1. Happens to be the same locator point. The radius is at 4. No, you square root the 4, right? So 2 to the right, 2 up, 2 left, and 2 down. Should you draw that circle as a solid circle or a dashed circle? It has the equal to bar, so it should be solid. Okay, the y is not alone like I circled in the first one, right? I can't use my shortcut. So I need to test a point. For a circle, always test the center. I will show you why. Remember, the center earlier was -1, 1. Plug in -1 for x and +1 for y. And what happens? Well, this whole thing becomes 0. That's the definition of being the center of the circle. That will always happen if you test the center. You will always get 0 on the side with the x's and y's. Then we have to decide if this is true or false. This one happens to be true. So since the center is true, I would lightly shade the center, or I'm going to draw some stripes. But then the final solution, you need to extra dark shade over where my stripes overlap. It's where the two inequality shadings overlap. That's the solution. You don't need to draw this big arrow saying solution, but you need to show it with extra dark or a different color. If you like to use colors, that's fine also. But the solution is that extra dark area right where my red shading is. So circles, test the center, and then it will come out to be an easy thing to check. Okay, that's it when it comes to graphing inequalities. So I wrote another example for you to try on your own. See if you can graph these two inequalities on the same set of axes, just like we just did. So start with the circle, and then you should pause your video, and when you unpause it, you will see just my circle. Okay, so the circle had a center at 2, -1. Remember, it's opposite of both. A radius of 3. It should have been dashed because there was no equal to bar. And when I test the center, I know everything with the x's and y's is going to become 0. 0 is less than 9. I didn't finish this yet. That's true. So I would lightly shade inside the circle. If inside was false, I would shade the outside, right? It's one side or the other. Okay, now graph your cubic. See if you can finish that graph. Pause your video. Okay, that cubic had a locator point at 1, 1. It also had an A value of 1, so try to make it look like a cubic. It has an equal to bar, so it's a solid line. And then I've got y alone, so y is less than. So from my locator point down, I would stripe down, which also looks like it's the right-hand side. But from the locator point, I went down. And then to answer the question, I really darkly, if I'm using pencil, or I shade it in with another color, the solution is just where the shading overlaps. So if I asked you, is 5, -4 a solution? you would go over to 5, 1, 2, 3, 4, 5, and then down 4, 1, 2, 3, 4, and you would end up not in the red. So a solution to the system is how I should have worded it. I'm just trying to squeeze in a quick question. Since that point is not in the red, you would say no. It is a solution just to the green one, just to the cubic, but it is not a solution to the system. Solutions to the system are all those red points that I shaded in. Hopefully this makes sense. Stop by at a Zoom meeting if necessary and get help anytime.